Welcome everyone to this explainer. Listen, if you're a middle school science student with even a tiny bit of curiosity about how the natural world is put together, you are in for an absolute treat today. We're going to look at the natural world not just as a habitat, but as this master workshop full of perfectly crafted biological machines. So let's dive right into this. So, I've got a question for you. What is the most perfectly engineered machine on Earth? Now, I want to challenge you to realize that the most advanced, intricate machinery out there, it isn't always made of metal and silicon. It isn't a $1 million sports car or the newest smartphone. Actually, some of the most masterful designs are crawling right outside your window right now. Or, who knows, maybe even hiding in the corner of your ceiling right now. Here is our workshop blueprint for today. We are going to explore 1. The arachnid blueprint, 2. Marvels of respiration, 3. The silk factory, 4. Arachnid variations, and finally, 5. The many-legged chassis. It's going to be a really fantastic comparison of these incredible crawling designs. Let's get to it. Section 1. The arachnid blueprint. Okay, so these creatures showcase some deeply purposeful craftsmanship. It's like a perfectly organized toolkit where every single specialized body part serves a very specific, purpose-built function for survival. Because arachnids actually have a liquid diet and sucking mouth parts rather than chewing ones, they use their chelicerae for seizing and crushing prey, and often for injecting powerful digestive enzymes. Right next to those are the pedipalps. These are innovatively engineered to guide food, dig, and even act as sensory organs. And because many spiders actually have pretty terrible eyesight, they're covered in setae. These are stiff bristles that act as highly tuned sensory detectors. They can literally feel the microscopic vibrations of a struggling insect caught in a web. Now, here's where it gets really wild. Their legs are just as specialized as their mouthparts. I want you to imagine trying to walk without any muscles to stretch your legs out. Sounds impossible, right? Well, spiders operate using something called hydraulic locomotion. They do have muscles to bend their legs inward, but they rely entirely on internal blood pressure to extend them back out automatically. It is just an astounding biomechanical feat. In fact, if a spider loses fluids and its blood pressure drops, its legs automatically curl right up under its body. Section 2. Marvels of respiration. So the natural world offers two completely masterful respiratory engineering solutions to breathe air without having lungs like a mammal or gills like a fish. On one side, we have book lungs, which are found in a lot of spiders and scorpions. These are absolutely incredible. They're made up of thin, flat folds of tissue arranged exactly, and I mean exactly, like the pages of a book. They're called lamellae. Air literally slips right between these pages to exchange oxygen and carbon dioxide with the blood. On the flip side, we have trachea, which are utilized by daddy longlegs, centipedes, and millipedes. This is a network of branching internal tubes that take in air through these tiny little openings on the outside called spiracles. It's a beautiful example of two entirely different, highly intricate methods of craftsmanship solving the exact same problem. Section 3. The silk factory. Think of the spider as a master chemical engineer. First, they have specialized glands in their abdomen that produce liquid silk. Second, this liquid gets squeezed through short, finger-like structures at the rear of the abdomen. Those are called spinnerets. And third, in literally a fraction of a second, that liquid is transformed instantly into a stretchy, solid thread. And the craziest part, spiders can actually produce different kinds of silk on demand. They've got a specific formula for wrapping prey, another one for building webs, and yet another for weaving protective egg sacs. I really want you to let this quote sink in for a second. Some types of spider silk are 5 times stronger than steel cable of the same size. 5 times. Just think about the sheer structural perfection and material strength required to manufacture something like that. And they do it at room temperature? It truly sparks this sense of wonder at the deliberate, purpose-built design of these tiny factories. Section 4. Arachnid variations. So let's look at some variations on this blueprint. Notice the mechanical difference in the jaw design between the two main groups of spiders. Over here on one side, we have true spiders, like the brown recluse or the black widow. Their chelicerae move side to side, kind of like a pair of pincers, and their fangs point inward and cross right in the middle. But look at the mygalomorphs. These are your massive tarantulas, like the ones found in the Amazon basin. Their chelicerae move up and down, with their fangs pointing straight down. They operate by literally stabbing downward into their prey. And when they're not using them, those formidable fangs swing up and tuck away like little pocket knives for safe storage. Now, how about harvestmen? You probably know them as the daddy longlegs. While they do have 8 legs, notice how their blueprint is altered. They lack that distinct waist that spiders have. Instead, their cephalothorax and abdomen are fused together into a single oval-shaped unit. They only have 2 eyes, and they completely lack spinnerets. No silk for these guys. But here is their most innovative engineered survival mechanism. Their primary sensory organs are actually located in their second pair of legs. And if they get caught by a predator, they have a built-in safety release. They can just detach that leg, run to safety, and continue to function totally fine. Imagine just popping off your arm to escape an awkward situation. And if that wasn't enough, they even feature built-in stink glands to emit foul odors to drive predators away. Continuing our look at these variations, we have scorpions and pseudoscorpions. Scorpions are heavily armored, solitary, nocturnal hunters. They are equipped with a potent, venomous stinger on their last tail segment, that's called a telson, and massive, crushing chelae or claws on their pedicles to hold their prey. And remarkably, female scorpions give birth to live young and literally carry them around on their backs. Pseudoscorpions, on the other hand, well, they're tiny, flattened arachnids that often hide out in the pages of old books. They don't have stingers at all, but they do have their own formidable venomous claws. And incredibly, they possess silk glands too, but the silk emerges right out of their mouthparts, so they can build these cozy little winter cocoons. Of course, we can't talk about arachnids without mentioning the microscopic multitudes, the ticks and mites. Some scientists estimate there could be up to 1 million species of them. Now, like the daddy longlegs, they have unfused bodies, but their design sequence is completely unique. Immature ticks and mites actually hatch with only 3 pairs of legs, right? And then they undergo this extraordinary structural shift to grow a 4th pair when they reach adulthood. Though they're tiny, they are perfectly tailored parasites, making them highly effective vectors for diseases like Lyme disease and Rocky Mountain spotted fever. Section 5. The many-legged chassis. So far, we've seen the compact 2-regioned arachnid blueprint. The cephalothorax and the abdomen, which relies really heavily on hydraulic pressure and exactly 4 pairs of legs. But when we look at the centipedes and millipedes, the myriapods, we see an entirely different mechanical approach. Their chassis is an elongated, multi-segmented locomotive design. They bring back the antennae and the mandibles for chewing, and they distribute their weight across dozens, sometimes hundreds, of highly coordinated legs. But hey, even within the myriapods, the specific functional differences are just astounding. Look at class Chilopoda, the centipedes. They're basically built like fast-hunting sports cars. They have a flattened body with 1 pair of legs per segment, making them super fast, wriggling carnivores. They even have purpose-built, poison-bearing appendages called maxillipeds to take down prey. In stark contrast, class Diplopoda, the millipedes, well, they're built like armored tanks. They have a rounded body with 2 pairs of legs per segment. They're slow, gliding herbivores that feed on decaying plants. And because they really can't outrun anything, they're engineered with an armored coiling mechanism to protect their delicate undersides, along with stink glands to make sure any predator that tries to take a bite immediately regrets it. So as we wrap up today's explainer, I really want to leave you with a provocative thought. When you look at these precise, tiny biological machines, from the hydraulic legs of a spider to the poison-tipped maxillipids of a centipede, what does their intricate craftsmanship reveal to you about the natural world? I mean, every single specialized feature we've covered today points to a world of deeply purposeful, deliberate design. The natural world is a master workshop, and honestly, we've barely scratched the surface of understanding its engineering. Keep looking closely at the world around you guys, and I'll see you in the next explainer.